So I hope it is audible and visible to all. If yes, so anyone can respond in the chat box so that we can begin with the class. Okay, fine. So now uh, we will start with the next topic. The next topic in module 2 is fast Fourier transform. Okay. So in the previous sessions, we have discussed about linear filtering methods based on DFT, right? So here we have used DFT, IDFT, linear and circular convolution to compute DFT, and we have successfully converted time domain samples into frequency domain samples, or frequency domain samples into time domain samples. But the problem is that it takes more time to compute if I use any digital processor. So that is what we have observed in the last problem which you have solved. So they have tried with the different methods to compute a given problem in a LTI system. So that problem takes much time, okay, to compute the given problem, just to convert from time domain to frequency, or frequency domain to time domain. So now, so to overcome this problem, we went through another system or another algorithm, and that is called as fast Fourier transform algorithm. So in short, we call it as FFT algorithm. So now, what is this FFT algorithm? So here, fast Fourier transform is nothing but it is an efficient implementation of DFT. Means here, DFT takes more time and needs more memory to compute a given sample from time domain to frequency domain. So when come to the fast Fourier transform, so fast Fourier transform also performs the same thing which has done by DFT. That is, it is also used just to convert the sample from time domain to frequency domain, or from frequency domain to time domain. But the difference is that here this fast Fourier transform can efficiently implement the DFT problems or the DFT computation. Okay, so here why we choose fast Fourier transform. So this is because here if the sample is very lengthy, then in fast Fourier transform, that sample will be split into two forms. Means the large or the length of the sample is split in two, or it will be divided into two forms, and those two which are divided, those two forms will be executed in parallel. I hope you guys get it. Okay, those two which are divided from the main sample will be executed in parallel, so that we can compute that sample much faster than DFT. Okay, so here another important thing in fast Fourier transform is that it uses, okay, a digital processor which uses inbuilt functions like a lookup table. I hope you guys known about lookup tables, which holds the known values in that table. So here fast Fourier transform uses such lookup table to compute the given sample. So thereby it uses less memory and executes much faster than the normal process, that is linear filtering methods. Because this linear filtering method requires more time and more space and becomes difficult if the number of samples are very lengthy. Whereas fast Fourier transform is capable of executing the samples much faster, okay, and also uses less time with less memory. Okay, so now the main application of fast Fourier transform is, so it is used in digital image processing. I hope you guys know about the digital image processing. So in digital image processing, it is used for filtering the image, remove the noise present in the image, like you capture the image in camera. So most of the images are processed using fast Fourier transform algorithm, because so this is more advanced in calculating or converting the time domain samples into frequency domain samples. And the another application of fast Fourier transform is it is also used in digital communication, yet wherever it requires the conversion between time to frequency or frequency to time in digital system. So this is about fast Fourier transform, and this fast Fourier transform is more advanced than the linear methods used in or based on the DFT. So now first we will discuss how this fast Fourier transform is more efficient in the computation of DFT. So which is given here. So that is the efficient computation of the DFT. Okay. So in this efficient computation of DFT, what we are going to discuss in this efficient computation of DFT, we are going to discuss radix 2, FFT algorithms. Okay, so radix 2 FFT algorithms for the computation of DFT and IDFT. Means using DFT we are converting time to frequency. Using IDFT we are converting frequency to time, but only using two algorithms. And those two algorithms are decimation in time and decimation in frequency algorithms. So now in this topic of module 2, that is the last topic, FFT, we mainly concentrate on decimation in time and decimation in frequency algorithms. Okay, so these two here, decimation is nothing but splitting the sample. Decimation means split the sample in two forms. So in respect to time and with respect to frequency. So that is what we are going to discuss here. So, okay, so now we will move on to the topic. We'll start with the fast Fourier transform. First we'll analyze how it is difficult to execute the DFT samples and how many multiplications and additions are required to execute or to compute the DFT, and then how it is overcome by using fast Fourier transform. Okay, so the name is itself the name itself suggests that fast is nothing but it works much faster than linear filtering methods based on DFT algorithms. So now we will move on to that topic. So now this is the topic which we are going to discuss. Okay, so that is fast Fourier transform algorithms. So in that first, as I said, we will discuss what happens in the direct computation of DFT. Means what is the complexity in the DFT, that is linear based method, and then we will discuss how this complexity present in the DFT computation can be overcome by using efficient implementation of fast Fourier algorithm. So now, as we know that, I hope whatever I said in the said right now understood. Anyone can respond here so that I can start with this. You guys got an idea what is FFT with respect to DFT? So anyone can respond in the chat box. Okay, fine. So now, so that is the theory-based explanation which I have given there. So now we'll understand how the direct computation of DFT has problems, and those problems is overcome by fast Fourier transform. So now, first in that computational complexity of DFT means once we computing the DFT using linear filtering method, what will be the complexity in that, and now how we overcome that. Now we know that by the definition of the DFT, x of k is nothing but summation of n equals to 0 to n minus 1, x of n wn raised to kn. So in this, x of k is the frequency sample or frequency domain sample, x of n is a time domain sample, 0 to n minus 1, these are the number of samples, wn raised to kn is the total factor, where k is the output sample from 0 to n minus 1. That is what we know in the DFT. So now, what is this x of n? So x of n is nothing but it is a real, okay, it can hold real or complex values, and w of n is a total factor. So sometimes it is also called as phase factor. Both are same here. So here x of n contains both real and imaginary samples. With respect to that, total factor also has imaginary and real factors. That is cos theta plus j sin theta holds both real and imaginary values. So now what I will do, so we will consider or we will expand this summation of x of k with respect to x of n with total factor, so which is shown here. So what we have done here, the frequency domain sample x of k is expanded from n equals to 0 to n minus 1. So what we got? X of 0 into wn raised to 0 plus x of 1 into wn raised to k. So it goes on up to x of n minus 1 into wn raised to n minus k. Okay. So here in this expansion of summation, so how many multiplications are carried out and how many additions are carried out? So this is what we are going to find out first. Okay. So then later on we'll move on to the FFT algorithm to overcome this. So now look at this. So here in this expansion, we have 1, 2, 3, 4 like this up to nth number of multiplications are there because the value of k varies from 0 to n minus 1. Nothing but, so here total n number of multiplications are carried out and 0 to n minus 1 number of additions are carried out here. So if I want to perform only for k equals to 0 term, if I substitute here k equals to 0, then what it does? It will perform n number of multiplications and n minus 1 number of additions, okay, including both real and imaginary values, or you can say that complex additions and complex multiplications. So that is what is shown here. So that is what we have said here. Therefore, what we need n minus 1 complex additions for one value of k. That is important here, only for one value of k. Suppose if I substitute the value of k equals to 0, it requires how many complex additions? N minus 1 complex additions. If I take n equals to 8, so 8 minus 1 becomes 7. So total 0 to 7 complex additions are required. Similarly, how many complex multiplications? If n equals to 8, so total 8 complex multiplications are required only for what? One value of k. Suppose if I take the value of k, range is from 0, 1 to n minus 1. That is nothing but, if I start from 0 to n minus 1, nothing but n number of values of x of k. Then how many complex multiplications required and how many complex additions are required? That is what we are going to show now. So if I take n number of complex multiplications required for calculating k equals to 0 to n minus 1 of x of k. This is nothing but if I want to compute the complex multiplications for n number of x of k, then we need n cross n, that is n square complex multiplications. So I hope you guys getting this. Okay. If I need only for k equals to 0 or k equals to 1, that is, if I need only one value of k, then I need n complex multiplications. If I need n number of x of k, that is, if k value is n, then I need n cross n, that is n square complex multiplications to find the complete x of k with respect to multiplications. Similarly, if I do number of complex additions required for calculating this much, that is k equals to 0 to n minus 1 values of x of k, means if the value of k equals to n, because here it started from n minus 1, or I can say that if k equals to n, complex additions are required, I need n minus 1 into n, because here for only one value of k, I need n minus 1 additions, which are written here. So I need n minus 1 complex additions for only one value of k. If the k value is capital N, means if k equals to n, then how many complex additions required? They are n minus 1 into capital N. That is, n square minus n complex additions are required to perform or to compute one complete DFT. This is very important. All these concepts are now we'll consult. Okay. From this, it is clear that we need n square complex multiplications and n square minus n complex additions just to compute one complete DFT if the value of n is provided. Okay. So now in this, now we'll go on depth to understand if complex multiplications, okay, so required how many real multiplications and how many real additions in that complex multiplication and in that complex addition. So before that, here we have taken if the complex multiplications required is n square, if the n value is 1024, 1024 are the number of samples given for the computing DFT. So if 1024 is the value of n, then 1024 square. If I take this, it becomes 10 raised to 6 absolute value. So we need 1 into 10 raised to 6 complex multiplications just to compute 1024 samples of the DFT. Similarly, for the complex addition, it becomes 1024 whole square minus 1024, which is absolute or nearly equals to, again, 10 raised to 6 complex additions. So total, this much of cycles required just to compute one DFT for using complex multiplications and complex additions. Just have taken one example to understand this. So now, next is, so before for going for the next thing, remember we need n square complex multiplication, n square minus n complex addition. If you want to evaluate 1024 points DFT of a given sequence, means here they have given instead of 8 point, they have given 1024 point, then we need 10 raised to 6 complex multiplications and nearly 10 raised to 6 complex additions. So now, we'll move on to using this concept. We'll move on here to understand this property. So now, what are the needs for efficient computation of the DFT? Means how to make this efficient for the DFT and what are the requirements or the needs to overcome this kind of problem. So now, so what I will do, so let us assume that the processor executes one complex multiplication in 1 microsecond. So what I said, I will take one sample, okay, or one complex multiplication, which requires 1 microsecond. Let one complex addition also require 1 microsecond to execute. Then the time required for computing how many 1024 DFT will be. So here complex multiplication into time taken for one complex multiplication plus complex additions into time taken for one complex addition. So here for complex multiplications which executes 1024 DFT, we need 10 raised to 6. And how much time taken for one? That is 1 microsecond. That is 10 raised to minus 6. Similarly for complex addition, nearly 10 raised to 6. Again, how much time takes? Again, it is 1 microsecond, which is given in the question. Okay, this is time taken for executing one complex multiplication and one complex addition, which is written here. And in general, we need for 1024, we need complex multiplications are 10 raised to 6 and complex additions also 10 raised to 6. If we solve this, we will get absolutely 2 seconds. So that is the time required to execute only one complex multiplication and one complex addition. So 2 seconds becomes very, very large time, okay, and requires more memory also to store the information. So now this is not possible practically to implement the DFT if the number of samples are 1024. So this is a problem which we are going to face in the direct computation of DFT, or this is the complexity. So now what is the need for efficient computation for this? So here now, so that we will go into discuss now. So first thing what I will do, so how many multiplications are required for the remaining process? That we are going to understand first. Then we'll switch to the need for the efficient computation of DFT. So now look at this. So in the direct computation of n-point DFT of a sequence, so here we will find out how many multiplications, additions, and trigonometric functions evaluations are required. That is what we are going to discuss now. Okay, for the direct computation in DFT. So first thing, we know n square is nothing but what? Complex multiplications. N square minus n is nothing but what? Complex additions required to compute n-point DFT. So now in this, what I'm going to do? In this, I'm going to find out in complex multiplication, how many real multiplications are there and how many real additions are there. Similarly, in complex addition, we are going to find out how many real additions are there. And then we're going to find out the trigonometric functions required or how much time is required to execute the trigonometric functions. Another important thing, in trigonometric functions, we need a complex multiplications and complex additions because trigonometric function involves twiddle factor. The twiddle factor Wn is nothing but what? Cos theta plus j sin theta. So cos theta and sin theta, they are nothing but trigonometric functions. So because of that, we are going to also find out how much time required for the trigonometric functions, to evaluate. This is what we are going to discuss now. Now first thing what I'm going to find out to determine the real multiplications, additions and trigonometric functions. First thing, we'll focus on real multiplications in complex multiplication. Complex holds both real and imaginary. If I found out the real part, the imaginary part will be the same. So first focus on real multiplications. We know that x of k is nothing but summation of n equals to 0 to n minus 1 x of n wn raised to k, where k varies from 0 to n minus 1. So now we know that x of n is nothing but holds real and imaginary function. So that's what we can write. X of n is nothing but xr of n plus j into xi of n. And twiddle factor also holds two forms, that is real and imaginary. That's what is split as Wrn of Kn plus j into Win of into Kn. So now let us multiply these two in the summation. What I will get? So this is x of k, summation of n equals to 0 to n minus 1. So x of n is replaced by this term and twiddle factor is replaced by this term, both holding real and imaginary values. So now using this, we're going to find out how many real multiplications and additions are required to compute direct DFT. Now here in x of k equals to, so multiply these two, what we will get? Here this is like a plus b into a plus b formula. So this is xr of n multiplied with wr of n, which is the first term. Then xr of n plus j of wi of kn. This is the second term, which is written here. J into w, this is the third term, which is written here. And the fourth term, j into j becomes j square, that becomes minus 1. So minus 1 becomes minus here. Then xi of n into wi of k. I hope you guys go through this. It's very simple. Simple multiplication like a plus b into a plus b. So here you got this term. So this is how we have separated both real and imaginary functions. So these two belongs to the real part plus j of imaginary part. Now in this, let us find out how many real multiplications and real additions are there. So this is first real multiplication, this is second, this is third, and this is fourth. So total we have 4 real multiplications. Then how many additions are there? So we have minus, this is one addition, that is this is second. So these two are belongs to the addition category. So here don't confuse with the minus sign. This is only sign, either performs addition or subtraction. So that's why don't confuse with this. This is one sign, this is second sign. So total 2 real additions are there. Now don't confuse with this one. So this is just to show that this belongs to complex. That's the importance. Plus will not be evaluated in the processor. Just to represent the complex numbers, that's why we show this plus for the users, not for the computers. So that is what is written here. Complex numbers are represented by real part plus j of imaginary part. This is real plus j of imaginary part. Okay. So this addition is never executed. Understood? Since it is just a way of representing complex numbers, means plus here will not be executed by the processor. This is just a representation so that we can understand or we can categorize this as a this number belongs to complex number. That's it. It will not be executed by the processor. So now from this we can say that it has 4 real multiplications and 2 real additions. This belongs to in what? Complex multiplication. Okay, here I'm showing this is what I'm considering it for from complex multiplications, which are n square. From that I'm getting real multiplications, then real additions. Okay, so from this what I got 4 real multiplications and 2 real additions. Okay, so now we know that one complex multiplication is converted. This is only for one complex multiplication. So what we got? We got 4 real multiplications and 2 real additions. Okay. Now, if I want for each value of k, for single value of k, we have n complex multiplications. Means now 4 is multiplied by n for the value of k1. Any one value should be taken here. At that time, we will get 4n real multiplications, 2n real additions. I hope you guys getting this. At this time, the value of k is only one value. Either from 0 to n minus 1, I am taking only one value. At that time, it is 4n, this is 2n. 4 is and 2 are taken from this multiplication, from complex multiplication. That you guys need to understand properly. For one complex multiplication, we need 4 real multiplications and 2 real additions. For the value of 1k with n complex multiplications, we need 4n real multiplications and 2n real additions. For the complete DFT, nothing but if the value of k is n, for complete DFT holds, k is also n, small n is also n, means total n into n. So at this time, written here, for n cross n, that is n square complete DFT, we need 4n into n becomes 4n square real multiplications, 2n square real additions. Hope you guys getting this properly. Okay. So this is for complex multiplication. For the complex multiplication, we need n square. What n it is? So we need one second. For complex multiplication, we need n square complex multiplication. For complete DFT, how much real and real multiplication additions required? We need 4n square real multiplications and 2n square real additions. Okay, I hope you guys getting. For n square complex multiplication, if I want to perform n square complex multiplication, then I need 4n square real multiplications and 2n square real additions. I hope you guys getting this. Okay, this is only for n square complex multiplication. Similarly, if I go for complex addition, so let us consider for complex additions. So now what we will get? So here we have taken 2 complex numbers. One is a plus jb plus c plus jd. So here one complex addition. For this this is one addition. These 2 are complex numbers. For one complex addition, we're going to find out how many real additions are required. So this is addition part. Just arrange real and imaginary here. So A and C are real part. JB and JD are imaginary. So now rearrange this equation. What I will get? A plus C, J of B plus D. This is what? One complex addition, only one complex. Okay. So now for this, how many real additions are required? We need only two real additions. And here, this is the only symbol to represent it belongs to the complex number. It will not be executed by the processor. This one. Okay. So now, for one complex addition, we need two real additions. So now for n square minus n complex addition, how many real additions are required? So that we are going to find out now. So here we know that one complex addition, two real additions are required. For each value of k, there are how many complex additions? N minus 1. So we will find out 2 into n minus 1 real additions. Okay, now for the complete DFT, nothing but when the k values ranges from 0 to n minus 1. So for n minus 1 value of k, how many complex additions are, real additions are required? 2 into n minus 1 into n. Okay, this is for the value of k. So we got 2 into bracket of n minus 1 into n. That becomes 2n square minus 2n real additions. So this much of real additions required to compute complex addition. So now, but still there are additions which are also present in complex multiplication also. There are 2n square, and here we got 2n square minus 2. Now total how many real additions are required? 2n square plus 2n square minus 2n. So totally 4n square minus 2n real additions are required. So now from this it is clear that how many multiplications are required for computing one complete DFT. So there are n square complex additions, then n square minus n square minus n complex additions, then 4n square real multiplications, then 4n square minus 2n, okay, real additions. So these are required to compute one complete DFT. Okay, still we have another one left, that is trigonometric function. Okay, so let us focus on that also. So we know that the total factor is nothing but e raised to minus j of 2 pi kn by n. We know that e raised to minus j theta is nothing but cos theta plus j sin theta or minus j sin theta. With respect to kn, we got this, right? So here cos of 2 pi kn by n is one trigonometric function minus j of, there is a sign, another trigonometric function. So totally we have two trigonometric values are there. So now to compute this two trigonometric values, okay, for the value of small n ranges from 0 to n minus 1, and for the value of k ranges from 0 to n minus 1, means n into n. So totally we need n square, that is wn raised to k and nothing but n into n. So n square different values are there, two trigonometric values are there. So totally how many we need? 2e cross n, that is 2n square trigonometric functions or values are required to compute one complete DFT. So the list is given here, which we have discussed. That is, so complex multiplications n square, complex additions n square minus n, real multiplications 4n square, real additions 4n square minus 2n, trigonometric functions 2n square. So these are the things which are required just to compute one complete DFT. I hope it is clear for everyone. If yes, just put a message in the chat box first. Do it first. If it is clear, put as yes. If you want to repeat this, I will repeat it right now. Do it first. Do it first because I have less than 1 minute. Those who will respond in the chat box,